Very bad. Get a small positive number? Get a small positive. 15. Positive 15. You can use one of two units. You can either call it kilojoules or kilojoules per mole. I tend to just use kilojoules after this because each of these terms are kilojoules per mole. And we actually multiplied out the moles when we didn't have to really. But each of these coefficients are ones. So you take 1 mole times that number, and the mole cancels out. So I think it's more correct to just say it's 15 kilojoules for the delta H. But a lot of people will write 15 kilojoules per mole, and it's fine. Is anybody not able to get 15? You're not sure why? Just take the total of the products minus the total of the reactants. There's only one reactant here. From the table values. So what that means is, if you if you dissolve 1 mole of ammonium chloride, then it's going to have to take in 15 kilojoules of energy to do that. If it doesn't have energy available to it from the surroundings to take it in, it just won't react. Nothing will happen. So, I've got one extension question on this. What about if we didn't have 1 mole of ammonium chloride? How about if we only had 8 grams of it? Would you be able to determine what the delta H is for only 8 grams of ammonium chloride dissolving? Could you set this up as a conversion? Would you do that? Yeah, we need a periodic table for this one to convert to moles. Now, I have to tell you, there's hydrogen, nitrogen, and chlorine. You need to look at a periodic table for hydrogen, nitrogen, and chlorine. You got some of them memorized because you use them so much, haven't you? I have to tell you, this is a shocker for some of you. If you have at least 4 or 5 or more molar masses memorized, you have crossed over. You are no longer cool. You're a nerd. Sorry. Now think about it. Let's see. Carbon, hydrogen, oxygen, nitrogen, now chlorine. I'm afraid you've crossed over. That, by the way, is an irreversible process. Yeah. Yeah. There's a chemistry student for you.
Okay, sum of the products minus the reaction total. What does that mean? Like,
There's something called Hess's Law, which we haven't learned yet. That's what I would be teaching on Friday if I was here. Hess's Law says that if you combine chemical equations with their delta H's together, and things cancel out and you get a new chemical equation, you could just add up the delta H's of those reactions, and that would be the delta H of the new reaction you get. I'm probably not making any sense when I say that. I don't know that I can justify why this works yet, but when we do Hess's Law, it should be obvious. And this is probably not a great example for me to do it with. If I took something simple, I'll do it on the next example. Okay, I'll show you what I mean. So anyway, this solution is going to look like this. It's going to be 8.0 grams of NH4Cl. Convert to moles, 1 mole. And then molar mass is 53.5. Now what's our next conversion? Right, it's that relationship between, for every mole of ammonium chloride that dissolves, 15 kilojoules of energy are taken in. That's a conversion factor that you can use. And this is simple, but I want you to see that because you'll need to be equipped to be able to do this with stoichiometry. You know, you'll have a stoichiometry setup that'll say something like, well, you know, if X number of grams of ammonium ion are dissolved, how much energy would that take? Well, you need to be able to do that. Include the thermochemistry data into a conversion. So it just looks like this, 15 kilojoules and every 1 mole. The moles cancel out and we're left with kilojoules. Now the answer to this is 2.2 kilojoules. Don't be surprised. There's a reason I'm having you do this one. Tomorrow, I'm going to have some real ammonium chloride powder, and I'll have water, real water, not that fake stuff you hear about, but the real thing. And I'm going to do this experiment. Now, tomorrow we're going to be talking about calorimetry and how you measure delta H. But we're going to actually do this. I'm going to measure out 8.0 grams of ammonium chloride. I'm going to dissolve it, and according to our rules for calorimetry, I'll see if we actually get 2.2 kilojoules. And do you think we'll be close? You'll have to come back tomorrow and find out. And it's hilarious too. Coffee cup calorimetry is the cheapest, most crude experiment you can do because we just go to the dollar store and buy styrofoam cups. But it works so well. It's remarkable how well that works with our El Cheapo thermometers and dollar store styrofoam cups. Man, we get really good data. It's cool. Here's one other exercise with delta H. I'm just going to ask you to take a moment and see if you can do. What we have here is we have a chemical reaction, a gas phase reaction, so everything is gas. When you look up the values, you're going to have, like there's going to be ammonium, aqueous, and gas. It's all gases in this one. I'm giving you the delta H for the reaction. But it turns out that this first reactant, ClF3, chlorine trifluoride, is not in the thermodynamic table. So what I'm asking is, what is the heat of formation of this substance? You'll know everything else, you just don't know that. Can you solve for it? And this is simple enough to do. You look at this and say, oh yeah, I can do that. But then it's really easy to make mistakes.
You don't have to. We do.
I think for all of our kilojoules and delta H's, out of the table, when you use the table, even if you get a decimal number, just round to the whole number. For these delta H's, that's good enough. You get an answer? Okay.
Yeah, the
How did you do? Negative 169?
Yes.
All right, can we do one more thing? Pause one more moment. So the last thing for today is another way to determine the delta H. Not only do we have the heat of formation table available for us to figure out what the delta H of a reaction is, sorry. By the way, we would consider this a theoretical delta H.